Okay. Well, welcome to our Facilitators webinar for NASA's Astrophoto Challenges. And let me first start with some introductions of who our presenters are from NASA's Universe of Learning. I'm Mary Dussault, and also with me are Erica Wright and Lucas Giuliano, soft G, I'm afraid.
Giuliano, yep, you nailed it.
Yeah, okay. And we're all at the Center for Astrophysics, Harvard and Smithsonian, which is one of the partners in NASA's Universe of Learning. And we're also the site where the MicroObservatory telescopes are operated out of. And we'll tell you a little bit more about NASA's Universe of Learning in a minute, and about how NASA's Astrophoto Challenges take advantage of resources from all these places. So let me just give an overview of the agenda for today. We're gonna have a little introduction, do some introductions. We just started with ourselves, but also to what NASA's Universe of Learning is. We'll give a brief overview of the summer 2022 edition of NASA's Astrophoto Challenges. And if people want to note in the chat whether they've ever participated in these before or not, you can just say yes or no. That would be of interest. This year's target is the star system Eta Carinae, anyway, Carinae. I never know quite how to pronounce that. And its wider environment of the Carina Nebula. We'll have a scientist view from Lucas of this area, all about, it's an area rich with star formation, life cycle of stars, and multi-wavelength astronomy. And we'll give you a tour of the actual Astrophoto Challenges activity. And finally, kind of introduce you to some resources that you can use if you want to engage your participants in this very exciting activity that's going to launch in May 2nd, and be occurring through the summer until July. So first, a bit about NASA's Universe of Learning, which is the host for NASA's Astrophoto Challenges. It's a STEM education public engagement initiative that's part of the NASA Science Activation program. So the partners in this STEM engagement initiative include the Space Telescope Science Institute, the science operations home of the Hubble and now Webb Space Telescope. They're the lead of NASA's Universe of Learning. Center for Astrophysics, which is the home of the Operations Center and Science Center for the Chandra X-ray Observatory, is part of the consortium. The IPAC, which is the Infrared Processing Archive Center in California, home of the Spitzer Space Telescope Data Archive, and our colleagues at JPL who engage lots of scientists in exoplanet science, which is another initiative of NASA's Universe of Learning, another content area, which we won't be talking so much about today. But essentially, all of these rich, science-rich institutions collaborate with educators and scientists to create experiences that help learners explore big questions, to experience how science is done, and to discover the universe with these incredible astrophysics assets. And NASA's Astrophoto Challenges takes advantage of data assets of NASA's Universe of Learning. So, as I said, this is a public participation. It's a participatory science engagement opportunity. It's going to launch, typically we're trying to get to at least a once-a-year schedule, and NASA's Universe of Learning may get to a twice-a-year schedule, but the last time was last summer, so we're now on a once-a-year schedule. The challenges, your access to the data and the activities launch on May 2nd, but the submission deadline isn't until July 31st, so you have lots of time to think about planning a program with a group of students, and submitting their astrophoto creations. So the program involves real telescopes, space telescopes from NASA, and telescopes on the ground. In fact, some telescopes that you can control yourself, the MicroObservatory robotic telescopes. Real data, participants learn and practice visualization techniques, and then you submit those. There's a form after you create your astrophotography challenge. How do those amazing images from NASA get created? Well, you and your participants can do it yourself. See what you can learn from the process of enhancing images. And then you submit them via the Astrophoto Challenges form. They get reviewed by a team of scientists and subject matter experts from NASA's Universe of Learning. And some of those entries, maybe 30 to 50, get recognized along with some commentary from scientists and subject matter experts. So it's a great opportunity to kind of get some feedback from NASA scientists and to become kind of part of a community that is thinking about learning from images. These are the goals, the learning goals that we have. You all as educators will probably bring your own learning goals to any participation your audiences have. So increased appreciation for NASA imagery, learning a little bit about the particular target of the Astrophoto Challenge. And as I said, this year, it's the big star-forming nebula and a erupting star, which we'll learn a little more about in a bit. To practice, certainly science educators are all around engaging kids in science practices. And so in fact, that's what you do in participating in Astrophoto Challenges. You do, kids will be doing some data analysis activities, learning science as they do science. And over time, we hope to build this schedule where people want to participate again and again in Astrophoto Challenges as part of a longer term effort to build the science identity, the feeling of belongingness, I can do science for participants. So those are our goals. And essentially, we call them plural Astrophoto Challenges because there is typically a set of two challenges, one using MicroObservatory, in which you have an opportunity to use real robotic telescopes to take your own images of the Carina Nebula and process them and enhance them. And then there's a NASA data challenge in which you have the opportunity to use real data from NASA space telescopes. And we actually combine it with some multi-wavelength, these NASA space telescopes across the spectrum, by the way. Sometimes we also include some larger professional ground-based telescopes as well, which we do this year. And we'll show you that as we move forward. So the Carina Nebula is a big star-forming region. And so you have, just to give you a glimpse of what you might be able to work with, on the left is an image taken with the MicroObservatory MicroObservatory robotic telescope there in Chile. This is a southern hemisphere object, or a southern sky object. So you have to have observatories that are further south than where we are in New England anyway, to see this object. And then on the right is another ground-based optical image with false color. You get a chance, students can use false color with our image processing tools. This one is from the Kitt Peak Observatory, one of the telescopes there. But we also have NASA data of the Carina Nebula across the spectrum. And this is an example of a infrared from the Spitzer telescope. I'm not going to say too much about it because I think we'll hear a little more about multi-wavelength astronomy in a bit. In addition to the wider Carina Nebula, this year's target also involves NASA data of this amazing star at this kind of near the center of this nebula called Eta Carinae, which has had this massive eruption, and we have data from across the spectrum. So that's the introduction, but we wanted to give Lucas a chance to talk a little bit about some of the ways he thinks about this region of the sky and how it works. So Lucas, I think I'm going to stop my share.
Okay, let me go ahead and take over. There we go. All right, let me just get this full screen while I'm doing that. I am Lucas Giuliano. I am actually a solar physicist at the Center for Astrophysics. So I primarily work in the solar regime, but a lot of the stuff that I do with the sun obviously translates over to talking about stars in general and just astronomy in general as well, because obviously the sun is a star. So I'm going to try to be pretty general, go through some of this stuff kind of quickly. If anybody has any questions or anything, I'd be happy to answer those as well. So just to start with some of the basics of stars and astronomy. So stars form from collapsing clouds of gas, like nebulae, like the object that we're talking about here. So space, for the most part, is very empty, very open. And you get these big clouds of gas that collapse down onto themselves and form stars. Stars are primarily composed of hydrogen and helium, makes up something like 99% of the universe, those two elements. There are traces of heavier elements that do play an important role in a lot of stellar stuff that I'll talk about later, but primarily these objects are going to be comprised of just hydrogen and helium coming together and exerting a tremendous amount of gravitational pressure because everything's being pulled into the center. And from that incredible pressure, we get heat and light. Eventually, the pressure becomes so big that fusion can occur in the core, and that's what's going to generate the majority of energy, heat, and light coming from the stars. Also produces a large amount of magnetic activity as well, but that's less important for what we're talking about today. So let's just briefly talk about what is light. You know, you could talk about light for years, but just to give a brief overview so we're all on the same page when we're talking about colors and spectrums and things like that. So basically, fundamentally, from a physics perspective, what light is an oscillating electromagnetic field, as you can see in this diagram. It's going to have an electric component, it's going to have an oscillating magnetic component, and it's going to be traveling in some way. Don't worry about that definition, that's not really important for what we're talking about today. For what I'm going to cover, let's talk about light in two different ways just to think about it. The first is photons. And thinking about light in photons makes the collection of data make more sense. So when you think about light as a photon, I want you to think about just a single particle, a little tiny BB of light that is traveling and has a particular amount of energy associated with it. The other way to think about light is as a wave, which makes it easier to talk about wavelength, obviously. So if you think about light as a wave, I just want you to think about it as an oscillation that has a particular wavelength associated with it. So again, with the photon, we want just a particle with distinct energy. And with a wave, that's how we're going to get our wavelength, which corresponds to energy, which is going to define what kind of light it is. So when we talk about X-ray, ultraviolet, visible, infrared, what we're really saying is what kind of wavelength does the light have? So something with a much longer wavelength would have lower energy and would fall in this area of the spectrum. And something with higher energy is going to have a much faster oscillation, going to have a much shorter wavelength, and is going to fall into this section in your higher energy stuff. So radio waves are about 1 kilometer to millimeters. Infrared is about 1 millimeter down to the hundreds of nanometers. Visible light, which is what our eyes can see, obviously with the colors and everything, ranges from about 700 to 400 nanometers. So with your longer wavelengths, your 700 nanometers or so, that's going to be seen as red. And as you increase in energy throughout the visible light spectrum, you're going to go across the Roy G. Biv rainbow all the way to blue and violet there. So that is what our eyes respond to. They respond to the particular energy or wavelength, however you want to think about it. And that is what generates color. but the same can be applied for the regions of the spectrum that our eyes can't see. So anything outside the visible light spectrum, our eyes aren't going to be able to see, but we have technology and cameras and things that can capture it. So when you see X-ray images of some of the objects we're talking about, our eyes wouldn't be able to pick up that light. We'd be able to see the visible light from the object, but that X-ray can be picked up based on our instrumentation. And so we can go further, we can go into ultraviolet, we can go into X-ray, and then eventually gamma ray. Most of this light's going to be collected by what are known as CCDs, or charged coupled devices. Basically, that is an array that just collects photons. If a photon hits the array, it generates a count, and that's what you're actually seeing in the images. Think of a whole bunch of buckets, and water droplets falling in them, and the camera, the image that you're going to get out, is basically saying how much light is collected in each of these buckets. So from there, let's ask what should be a really simple question, but is actually pretty complicated and gives us a lot of insight into how color matters so much in astronomy. What color is the sun? So obviously people have, drawn the sun, they know the sun, they're, a yellowish orange type color, you draw the sun up in the top right corner of your drawing or whatever. But it's actually a much more complex question that kind of gets into why color and wavelength matters so much in astronomy. So with the sun's, it's kind of a trick question, because the sun isn't just one color in the way that something else might be one color. So when we see color here on Earth coming off an object from, a blue piece of paper or something along those lines, what you're seeing there is reflected light. What's happening with the sun is it's actually emitting its own light. It's called black body radiation. So what the sun is doing is not just emitting light in one particular wavelength with one particular energy. It's actually emitting a broad spectrum of light covering a wide range of energy. So here's a plot showing the sun's emission. So this is all the light that's being emitted from the sun as a function of wavelength. And this is just in the visible wavelength. It is no coincidence that the sun peaks in the visible wavelength and that we can see in the visible wavelength. It is a fact of evolution that our eyes can see visible light because the sun peaks in the visible light. So it's not a coincidence that these two things line up. And the sun is going to peak in right about the green area, maybe a little more towards the blue, but really it's peaking in this, 500 or so nanometer wavelength. That begs the question, why does the sun appear yellow-orange in the sky as opposed to green in the sky? And that just has to do with the scattering of the atmosphere. It's known as Rayleigh scattering. It's the same reason that the sky appears blue. So because the atmosphere reflects higher energy particles more than it reflects lower energy particles, a lot of those blue photons that in that wavelength regime get scattered out, and then we see them as blue because they hit the atmosphere and then come down to our eyes. But that light from the sun isn't going to be visible as part of the sun because it's going to be scattered. So instead, we see a shift towards this region of the sun there. And what properties make the sun, which again is a star, and I'm going to talk more broadly about stars in a minute here, but let's talk about what properties make it peak here. It's not just random what color stars happen to be. The biggest one is mass, which is going to dictate the size and the temperature. Next up is elemental composition, and I'm going to talk very briefly about spectroscopy on the next slide there. Basically, what makes up the star is going to determine what colors are actually in the star. And then the final thing is just the equation that actually dictates this is called Wien's law. It just says that the max wavelength is proportional to this constant divided by temperature. So it is really the temperature that dictates what color it's going to peak in here. So just some real basic spectroscopy, not going to go too far into this. What's really happening here when we see light is we are seeing the transition of electrons within the atom. So take your most basic understanding of what an atom looks like, right? You have the core with your neutrons and your protons, and you have these electrons kind of circling around them at different energy levels. It's called the Bohr model. This is, one of the more simplified ways of thinking about atoms. What's happening is as these electrons gain or lose energy, they're going to throw out photons proportional to that amount of energy. So if energy were to come into this, which I believe is carbon, this electron could jump up in energy level and absorb some amount of light. And then if this electron were to jump back down in energy level, it would emit a photon of a very specific wavelength / energy level. So each element has its own unique spectrum that produces a set amount of certain colors. And each element has multiple energy levels. So it's not just one element producing one color. Each element is able to produce a whole bunch of colors based on the properties of the atomic physics stuff. So here are just some examples. Hydrogen, very basic, one of each, still produces different colors that are very unique to hydrogen. So as astronomers, we are able to look at these wavelengths and determine what elements are present. And then if you get a little more complicated, you have carbon, which has a lot more. And then obviously as elements get more and more complicated, you have more and more of these transition lines. But this is where the color is really coming from in stars, as these transitions occur based on the elements that are present. And so stars are really this broad composition of all of the elements undergoing these transitions. So here's the sun, which is what I study. And I just want to show this because this is using an instrument that shows the sun in a whole bunch of different wavelengths. So up in the left, we have our higher energy level. Down here, we have our lower energy level. And I won't play this whole clip, but I just wanted to show this to point out the importance of wavelengths in astronomy, because as these videos play, you can notice that it's easy to see different features of the sun based on what color / wavelength you are observing in. So for example, down here, it's much easier to see sunspots in active regions, these parts of the disk. Whereas if you want to see more of the corona, you could look at this wavelength. So I just want to highlight that different wavelengths are able to see different things in the sky. Ignore that, that's just part of the satellite. All right, so let's talk about how this relates to stars specifically again. So each star is going to have its own particular spectrum, and that spectrum is going to peak at a particular location, like we looked at with the sun. So if you have something like the sun here in the center, that's going to be peaking right at the visible wavelength, and that's going to be, about 6,000 degrees Kelvin. If you have a cooler star, that's going to be peaking more towards the red wavelength, and is going to be a little bit cooler. You'll still get some of the other colors in there, but that's going to be shifted more towards the infrared and towards that direction. You have a blue star, which is significantly hotter, and I'll talk a little bit more about what makes a star, the particular color and mass and things like that in a second. But for a blue star, you're going to see that peak happens way further out in the ultraviolet, most likely here is what this is showing. And you'll still get, all the colors of the visible light spectrum there, but the peak is going to be moved to the side. So we're going to see it as a blue star. So let's talk a little bit about what makes these properties and what we can learn from these properties about the evolution and lifetime of stars. So I've said this a lot already, but the mass, size, temperature, color, brightness, lifetime are all really intrinsically linked. These aren't variables that you can really change around very much. And what I mean by that is the most important property of a star is its mass. And that's going to be determined by the initial amount of gas present during the formation in the nebula. So once that amount of gas is determined and starts to collapse down, that is going to determine what the mass of the star is. The mass of the star is going to determine the size of the star. And the size of the star is going to determine the temperature of the star. And the temperature is going to determine how bright it is and what color is the brightness in. And smaller stars also burn significantly longer than larger stars do. So all of those properties that we're talking about that can be different across stars are really just determined by how much stuff is in there. In terms of the life of stars, I have a picture I'll show in a second, but basically a large star, when it dies, what's going to happen is all of that fusion that's occurring in the core of a star is going to burn itself out. And then there's not going to be an equilibrium of pressure, and that star is going to immediately collapse in on itself. There's no more of that outward force to keep it together, and it's just going to collapse into itself and then rebound back out and supernova. Smaller stars, on the other hand, like our sun will, tend to expand and then contract because there's not quite as much mass outside the core. it doesn't immediately collapse in. And instead, what it does is it expands and becomes a red giant, and then slowly contracts into becoming a white dwarf. It doesn't undergo that supernova process. So here's a nice picture showing what the life cycle of stars are. So first, the star is going to form in this nebula region, like the one that we're talking about today. All of that gas is going to come together, and depending on how much gas there is there, that's going to determine how big the star is. And if you have a star that's between half a sun to about 10 times the mass of a sun, as that sun burns through all the energy at the core, it will expand into a red giant and then slowly form into a planetary nebula and produce a white dwarf. And then the cycle kind of continues. The gas from there forms into another nebula, starts to condense down. You can see it just kind of cycles through. However, if you have a much larger star, if there's a lot more matter present to begin with, what's going to happen instead is when that star burns through its energy, it's going to expand and then rapidly collapse down into becoming a supernova. And the remnants of something like that could be a neutron star, which is just a significantly more dense and bright version of a white dwarf. Or this is where we get black holes from, where it just becomes so dense, it kind of tears a hole in the universe as we know it, more or less. And that brings me to the Heartspring-Russell diagram. So this answers the question of what happens when we organize stars by these properties we're talking about: temperature, wavelength, color, and then luminosity and brightness. It gives us this really good insight into how stars evolve and what their lives are like. So this band here, let's just, down here is temperature or color, whichever way you want to think about it. Again, blue is going to be your hotter, red is going to be your cooler down here. So if you compare the temperature or color of the stars to how bright they are, this pattern emerges. So imagine you took all the stars in the universe and you plotted them on this. What we would get is the Heartspring-Russell diagram. What this shows us is the majority of stars in the middle of their lives fall in this band known as the main sequence, which shows us that these kind of stars typically have this brightness, these kind of stars have this kind of brightness, and they all fall within this pattern. When stars evolve, they kind of move off the main sequence. They would first expand into giants or supergiants, and then they would collapse back down into white dwarfs. So this chart kind of shows just a snapshot of a life cycle of all of the stars, where it would start on the main sequence, it would move off, and then it would fall back down into this region. So yeah, we have our white dwarfs down here. Once they have burned through everything and are done, they have our red giants over here, and your supergiants are going to come from your bigger stars. So this brings us to the objects that we're talking about here, the Carina Nebula and the Eta Carinae. So this is a look at Eta Carinae, the star that we're talking about here. And this is showing it in different wavelengths to show things that are visible in different wavelengths. So in X-ray, you can't see out that much, but you can see the bright, central part of the star. That's because the star is really the only object there that's going to be emitting very, very bright in X-ray, because X-ray is higher energy, whereas some of the cooler gas around that isn't going to be emitting as much. Whereas in infrared, that's going to be the opposite. You're going to see a whole bunch of the gas surrounding it because that gas is able to emit at that wavelength as well. And then visible somewhere in between where you can see the gas, but the star is emitting significantly brighter in visible than the surrounding gas cloud around it is. From my understanding, I'm not an expert on this object. It is a star system containing at least 2 stars. So it's not entirely clear how many stars are there. There's definitely at least 2. At this point, it is a luminous supergiant. So it's about 120 to 150 times the size of the sun, and somewhere on the order of 10 million times brighter. Don't quote me on that, but on the order of millions and millions of times brighter. So scientists don't really know exactly what produced this pattern, but it was some combination of supernova occurring within a star system. So that evolution that I talked about becomes a lot more complicated when you have multiple stars in the mix that can expand and eat each other up and move around. So that's really why this produces such an interesting looking pattern, because there was at least 2 stars and one of them died and started to go through the next steps of stellar evolution there. So produces this really cool kind of swirling gas pattern that you can see in all of these. And here's just some pictures of the region. So This is just the one that I found on Wikipedia, but this is one that I was able to play around with myself and just change the scaling a little bit. One thing I didn't really talk about a lot that is relevant to this is most astronomy images that you're going to see have what's called false color. So it's not necessarily representative of the actual wavelength of the light in the image, but is something that is assigned within the processing to allow our eyes to be able to see it correctly. So this image on the right, I made blue because it's a nice scaling and it makes everything very visible, but this isn't necessarily, you know, blue light, 400 nanometer light that is being emitted by this object. It's just a way for us to be able to take a look at that and see it within our own eyes, because we obviously can't represent X-rays or infrared and be able to see it, you know, in an image with our own eyes. And then just here's another one. So this is more of the nebula, and then this is a look at the star itself, you know, very bright in the middle of this big surrounding gas cloud. So that's what I had about stellar evolution. Do we have any questions or any other things we want to talk about with that? Back to this picture because it's the coolest.
Yeah, thanks, Lucas. If folks want to write questions in the chat, I have a question which you may not know the answer to. So the Eta Carinae star, the star system, I guess is right. We don't know what it. If it you said it's like tens of million, 50 million, 100 million times brighter than the sun. So it must be much, much bigger because those things are all linked. Right. Is it about to go supernova?
Yes, I'm not entirely sure on the history of it. What I do know is that there was a big observation of this object in the 1840s, I believe, where I don't know if it was a supernova, but some sort of transition occurred. Again, it is complicated because we're talking about a star system with multiple stars, but at least something occurred there where one of the stars started to supernova or expand, or something along those lines. And all of a sudden, that what is normally a magnitude 4 star, which is just a measure of the brightness, where the higher the magnitude, the less bright the star. All of a sudden, that star, which was normally visible with the naked eye, but not super bright in the sky, became the brightest object in the sky for 10 to 15 years in the 1840s. That is because something happened a long time ago, and that light was just reaching us, where all of a sudden it became significantly brighter because of all of that energy that was released within that event. So that is why it is this bright now, because all of that energy is still reaching us from whatever occurred in that event a long time ago. However, the star itself is also, the main star within it, part of the star system, is also fundamentally brighter than our sun by a significant amount, but is far enough away that we're not being, constantly blinded by the light coming from that. It's about 8,000 light years away, so it's not quite as bright in our night sky as you would expect for an object that's millions of times as bright as the sun.
Great. That is fascinating. I wonder what it was. I wonder if people noticed this in the 1840s. I mean, obviously people didn't know about it, but I wonder.
You kind of had to.
If non-astronomers noticed it.
Yeah.
Star. Yeah. Awesome. Okay, if folks don't have questions, we'll kind of dive into what you get to do yourself, just as Lucas did his own processing of this data here. And I think I have to take the reins back here.
There you go.
Okay, let's see. Somehow I've lost my mouse. I'm going to try and share again. Eric, if you can tell me if we're still seeing a black box.
We are.
Okay. I'll have to, okay. How about now?
No
Still?
more. Gone now.
Isn't that weird? Okay, well, okay. So the challenges are hosted at the MicroObservatory website. And this is where it becomes tricky doing full screen and that black box, because I want to go to different URLs to show people here. Here we go. Here we go. So the NASA's Astrophoto Challenges are hosted on the MicroObservatory web pages, which are just microobservatory.org. If you go to those, this banner will link you right to the NASA's Astrophoto Challenges. And the web page has lots of instructions about how to participate. And you can see there's two challenges: the MicroObservatory challenge, in which you're using the MicroObservatory telescopes that I showed a picture of earlier to take your own data, or the NASA data challenge, where you're getting to use data from these multi-wavelength telescopes, each of which detect a different energy or wavelength, as Lucas talked about. So we'll take a look at that in a minute. Let's see, I think what I want to do here, tab, is give you the sizzle video for this year's Astrophoto Challenges, which kind of gives you the overview of the data you'll actually be looking at. So this is something you can introduce the project to your learners with, and then we'll actually go and I'll show you the easy to use image processing tool that you and your students can use to enhance your own data. So here's the sizzle video, and I think I've shared my sound, but now I don't know, so I'm going to stop. Sorry about that. I'm going to stop and do that again. Yes. Share. Okay.
Images of space can be amazing, but have you ever wanted to make your very own? NASA's Astrophoto Challenges invites you to do just that. You can select data from telescopes on Earth and in space, choose colors to apply, and produce your very own expression of the universe. For this year's challenge, we take you into the gaseous and dusty embers of the Carina Nebula, where new stars are being born, and one star in particular, the erupting Eta Carinae, is nearing the end of its life. In the MicroObservatory Challenge, you get to control an Earth-based robotic telescope to take your very own image of the Carina Nebula using visible light. In the NASA Datasets Challenge, you have a selection of images taken across the spectrum of light, X-ray, visible, and infrared, that you can mix and match into your own unique view of the Carina Nebula. Or you can make your own image of the iconic erupting star system Eta Carinae with additional data.
Or you can make, I'm not sure why this is not running. Well, or you can use the data, and we'll show you that right now. So I'll just stop that. Okay. Taking your own image with the MicroObservatory telescopes, you will use the Observing with NASA portal, and this allows anyone with an email address to take their own image. The process was shown in that little video here. There's a control telescope tab, and a target list, and the Carina Nebula will be highlighted once the challenges begin to take that image. You send your request, you specify a field of view and whether you want images that use filters, just like the Hubble telescope does, to only let through the red light, only let through the blue light, only let through the green light, and then combine that data into a representative color image. Or you can just take a single image with no filters. All you need is an email address, and you can, that image would be emailed to you. On the other hand, the challenges also, we provide some sample microobservatory data. So if you did this in a one-class workshop, you wouldn't have to wait till the next day, which you will have to do if you ask for the telescope images. Let me get back to, all right. So this is the kind of data that comes back from the MicroObservatory telescope. This is actually data of the Carina Nebula. And when you get your email, and the NASA Astrophoto Challenge webpage connects you to this JS9-4L, which is our browser-based image enhancement tool. You don't need to download any software. You can do this in your browser. And there are lots of video tutorials about how to go from what looks like a black and white image without much detail to a gorgeous astrophotograph that you can submit to the challenges. Now, these images, as Lucas described, are really numbers having come from the telescopes. I can, if I use this pixel table, you can see every place I put my cursor, there's a number under it. And here where that bright star, millions of times brighter than the sun is, the pixel number for MicroObservatory is maxed out. MicroObservatory has a maximum pixel value of 4,095. And you can see, in fact, that's so overexposed that that light has saturated down the detector here. So images are really numbers. Kids can learn about that. And what we can do is enhance the visualization of that digital data. You can view some of these tutorials and find how easy it is to start to enhance this image. I'm just going to kind of do it quickly here. So you can see here's that Carina Nebula. It's kind of upside down from where the way we've been seeing it. You can colorize it red, and I actually have 3 images open in this browser. I did the same for a green image from the MicroObservatory telescope and the same from a blue image. And so there are lots of tutorials to learn how, and I would recommend that before you do this with kids, you try it yourself, use some of these tutorials and learn how to enhance an image. The thing that NASA astrophotographers and amateur astrophotographers like to do when they have images in different wavelengths is blend them together to create different kinds of effects. And I'll use NASA data to show you that, that process. So I'm going to go to, all right. So once again, this is the Eta Carinae star system. I have data, again, this is the Astrophoto Challenges version of JS9, but it's not, I've loaded our Eta Carinae data into this. The data isn't quite ready for the challenges, so it wouldn't be publicly available to you yet until May 2nd. But you see, once again, the raw data, when you open it up in an image processing tool, doesn't look very amazing. If you open up the pixel table, again, you can see out here where it's black, the numbers are very low. Here where the Eta Carinae star is, actually the number is 280,000, very high. So great big difference between the brightness values as shown by the Hubble Space Telescope, this optical image. The tools to enhance images are very easy to use. Here's a slider to bring the brightness. Whoop. And suddenly I have an image that looks more like some of the NASA data. I can use these color tables so that the brighter to choose this using what's called false color, or just colorizing the image according to assigning different brightness values to different colors can get effects that are great. And I could also open up, take a look at a Chandra image of the same region. And you'll remember from Lucas's talk, the Chandra image has all this hot gas, X-ray, emitting X-rays all around, and looks quite different than the Hubble optical image. And so students might want to blend those two images together with something called a blend tool. And there's also a video tutorial for using the blend tool. We've found that students are very good at, once they get the hang of blending images, at making an incredible amount of creative astrophotography creations. So I'm going to blend that this optical image that we're looking at now and that Chandra image by clicking those two images. I also have 3 others open here, but I'm only activating those 2, blend them. And again, you can see that the X-ray hot gas is surrounding this erupting star area. So it's not in the same region, but you can get a wonderful image. You can then save that image as a PNG file. And that's the image that you can, oh, it doesn't go over. Isn't that weird? Okay, I see. Anyway, I have an image of that on my desktop that you can submit to the challenges. So let me just, I see that we're getting to the end of our hour, so I want to go through the submission form, which will also be linked from the Astrophoto Challenges page. Essentially, once you and your students have created images that they want to submit to the challenge, you click on the submission form. We'll need an email address. If kids are 12 or under, you as the teacher might want to do the submission form. We're not allowed to collect personally identifiable information of kids under 12. So you can do that. You select whether you've used MicroObservatory data or NASA data. You tell us, you upload your PNG file that you made using the JS9 tool. You tell us a little bit about how you processed your image. And if you have any questions about Eta Carinae, you can ask them. And we have follow-up programs of scientists from NASA's Universe of Learning who are will be talking about images and answering some of those questions that come in. Same for if you get NASA data challenge, you upload your image, you select whether you use the Hubble data, the Spitzer data, or some of the other data. Tell us a little bit about how you processed, whether you have any questions. And important for you as educators, have your participants be sure to identify the name of the school or workshop site, because we do like to recognize schools that participate in the challenges. And so that kind of ups the probability of students from your group being recognized in in the final challenges if we have the name of a particular institution where kids participated. Okay. Finally, we want to show you some, I think Erica has some resources to use to work with kids, and I apologize, Erica, for leaving you 3 minutes left.
That's okay. And hopefully you'll all bear with me. I'll go as quick as I can. We won't keep you more than a couple minutes past the hour. As soon as Mary pulls up my slides here. So just for a sample activity sequence that you might want to use with your students, and all of these activities can really be scaled up or down depending on the age of your students. So Mary showed you the sizzle reel for an introduction. We also will be putting out shortly a video with a number of scientists talking about Eta Carinae and the Carina Nebula in a little bit more depth. That's another great opportunity to kind of introduce this object and what they'll be exploring. So one or both of those two videos are great ways to introduce the challenges to your students. Then we have an activity called Kinesthetic Telescope. This activity really helps to reinforce where this data is coming from. So before the activity, most students think about telescopes as something that magnify light or magnify objects, but rarely do they actually mention light. But after participating in this activity, which is a great opportunity to get up and move around the classroom or go out in the field if you've got a field, they start talking about light and how it's traveling through space. They talk about detectors that we just mentioned, that both Lucas and Mary have mentioned as a place that is gathering light. So it's a really great way for students to really get an introduction feel of how telescopes work and where that data is coming from. After that, when we're facilitating activities, we like to do some activities around this images are data idea that both Lucas and Mary mentioned again, right? So we've got a couple an activity here about decoding starlight, or from pixels to images. And this tells you a little bit more about that data coming from the telescopes. And then Mary showed you that pixel table in JS9, understanding what those pixels are really telling you. So there's a great activity here for students. I think is this the battleship one, Mary? I've got myself mixed up. So yes, there's a battleship activity, and we all love a good game of battleship, to start understanding how much light is on any given pixel. And it's a great reinforcer of that pixel table that Mary showed you, and what these images, what this data really is, right? That it's numbers, it's the amount of light. That each pixel is one of those buckets that Lucas was mentioning at the beginning. Then I might have missed mentioning this. This can be a 2 to 3 day sequence. You can cut a few things out if you don't have the time, but this is really if you want to give a holistic picture of all of these concepts. After we kind of do those two really good introductory video opportunities. Oh, Mary's astropoetry.
Sorry, I'm in the wrong activity. Yeah, I skipped ahead. So sorry.
We like to do an instructor-led overview of image processing. So as Mary mentioned, there's a lot of tutorials to give you a sense of what's going on. There's also more videos on our YouTube channels if you want an in-depth dive into image processing. But in addition to that, we also have written guides on our training and resources page that you can hand out to students after you kind of walk them through the process first. As we mentioned, honestly, I found students are better at picking this up than teachers and adults. Many of them are less afraid to kind of dive in and start processing. And Mary's showing you here on our MicroObservatory site where you can find a number of these activities. So we've got the challenges with written guides to them. We've got the kinesthetic telescope. On this page you're seeing, we also have a couple extension activities that you might want to use with your students. If you've got some opportunities to get creative, astropoetry there is a really great extension to help students kind of start diving in and describing what they're seeing. It's a really great opportunity to do that. But back to the main sequence of activities that we think puts together a great 2 to 3 activity sequence class period. After your students process their images, we like to do a gallery walk, whether that's on your computer or printed, have every student pull up the images that they process and walk around as a group, pointing out different features that you notice, having students highlight why they made those images look the way they did. They can really surprise you in their image processing and what they discover. After that, to kind of wrap up and really reinforce all of what they've been doing, what they've been processing, why, there's some great Eta Carinae visualizations and additional resources. I think Mary's got a link to that somewhere for me. As part of our NASA's Universe of Learning, we've recently put out a great visualization of this. And so this is a great way to, after they've all processed and had this introduction, dive deeper and see what they found in their images. And then, as we mentioned, you're going to want to submit this as a group. Make sure every one of your students submits this. You have more likelihood that somebody will be selected as a highlighted entry in our image processing at the end of the challenges. So those together makes together a really nice sequence of activities. As I said, you might want to pull one or two out if we're short for time, and they can all be kind of scaled up or down depending on the age of your students. We also have, oh yeah, go ahead, Mary.
I was just going to say, to answer Tom, who's driving, yes, we will send out links to all these activities for the registrants. Yeah,
we will be sending out a follow-up. So there's a few extension activities and resources you might want to use with your students. I mentioned Astropoetry, Universe Unplugged. I think Mary put that on the screen for a moment. Has a full Eta Carinae resource collection, so you can learn more about the object. You can create your own exhibit. On the right here, you see a few images of exhibits that past participants have created. Students love seeing them up. The Astropoetry is a great way to get a label for each student's image. And we also have a whole set of community programs of other ways you might want to dive even deeper into using NASA's Astrophoto Challenges and creating a whole set of curriculum around it. So that was a really quick dive through of some activities you might want to try, and we will be sending this all out when we're done here in the next day or so with all these links to every activity you might want to try. All right,
great.
Back to you, Mary.
All right. Well, thanks for that whirlwind through the resources, Erica. Sorry, but again, we in an hour we kind of went quickly through this, through what the target is, what the challenge is, a little bit some about the science of color and the science of detectors and energy and how the telescopes are collecting wavelength from these different colors of stars and nebula, and then quickly through the tools that you actually use to create your own images. These are very easy to use tools. I really encourage you to try it out yourself, to go to the archive, the NASA's Astrophoto Challenges from the past that have NASA data, but not of Eta Carinae, are always available, and you can practice using those tools so that you'll be ready, you and your students will be ready to make the most of the Eta Carinae data, which is a really exciting set of data from the Spitzer Space Telescope, the Hubble Space Telescope, the Chandra X-ray Telescope, and other telescope data as well. If there's any questions, we can take them, or we'll stop for now and send you some follow-up material. I guess we'll send you some follow-up material. Thank you guys for your for attending, and we really hope that we'll get some submissions from Oregon and from I think there was Massachusetts Place, Milford close by, and
Maine and California.
Maine, excellent. We want to get your submissions. So if you want to reach out to any of us, here's our email addresses. ewright@cfa.harvard.edu is Erica. I'm mdussault@cfa.harvard.edu. And we look forward to your participation.